chemical equilibrium. So equilibrium, if we define, it is the state balance where two opposite forces are equals to each other. Like if a box is there and you are applying the force 1 and force 2, and if F1 equal to F2, then the box is at rest. So here this box is in static equilibrium. Because box is not moving. Similarly, so this is the buckets and this here is the pipe. So the equal amount of water is adding to the buckets and the same amount of water is removing from the bucket. Level of water neither rising nor decreasing. Movement of water molecule is happening. This type of equilibrium is called dynamic equilibrium. So we can say water level in bucket is in dynamic equilibrium. So in terms of chemistry, what I think that is the equilibrium happening that we call chemical equilibrium. Chemical equilibrium. Suppose N2 gas combustions to give ammonia. So what's happened? You can explain this as like here one ball is here, and if you rotate this ball, this will go here, and again it comes to here, and after that it's decrease the speeds, and finally it will stay at hello balls. Means this is the stable position of ball. So similarly, when you when the combustion reactions happen between nitrogen and hydrogen, they will form the ammonia. Then ammonia So they pour in this direction, this forward direction, and after that when ammonia forms, it again decomposed by backward reactions to give hydrogens and nitrogens. And after that, there will what happened, both forward reactions to ammonia and backward reactions to decompose N2 and H2 become same and will stay at equilibrium points like this hello ball. So past it will go this forward reactions, and after that backward reactions, and after that it will come to the stable state at this hello ball. So this is the stable point. So similarly, the equilibrium will happen. It will first form ammonia, and after that ammonia decompose to give this nitrogens and hydrogens, and after that no formation of backward and uh, forward will happen, and it will stay at a states which is called equilibrium positions. But like this ball, these stable positions, so this comes to that positions. So that positions is called equilibrium positions, or it attain the equilibrium. So definitions we can say, definitions of chemical equilibrium. It is the state at which the rate of forward reactions and the rate of backward reactions or reactions become equal, or in concentration term we can, or in concentration terms you can say the concentration of reactants and the concentration of products, the concentration of products do not change with times or remain constant. So the rate of forward reactions to pour ammonia and rate of backward reactions to decompose N2 and 3H2 become same. So that point we can say it achieved the equilibrium. So it is the state at which the rate of forward reactions and the rate of backward reactions becomes equal, or the concentration of reactants and the concentration of product do not change with the time. So at that point we say it achieved equilibrium. So law of mass first we will study the characteristics of chemical equilibrium. Characteristics of chemical equilibrium. What says it is dynamic dynamic in nature. So equilibriums can be two types, statics and dynamics. So this type is statics. Here the box is not moving, but here the water level is the movement of water is happening, but the level of water is remaining constant. So here this type of equilibrium is called dynamic equilibriums. Similarly, like here the ammonia and hydrogens, so nitrogens, ammonia are combustions to give ammonia, and ammonia after that decomposes to give nitrogen and hydrogens, and at the some points they will come to that point where that formations of ammonia or decompositions of ammonia is not happening, and they achieve an equilibrium points. So here uh, the movement of the molecules is happening, but it looks like it's not happening because they achieve the equilibrium. So this is a type of dynamic equilibrium. So the chemical equilibrium is dynamic in nature. That is rate of forward reactions equal to rate of backward reactions. Next point, it can be achieved from either sides. That is, like if you say nitrogen gas plus 3 hydrogen gas, the combustions to give 2 ammonia gas. So this can be, so we are doing the combustions and we have equilibrium, we are doing the ammonia. So this we can write in opposite directions that ammonia is achieving in both the cases, it will not affect the equilibrium point. So either we can write express this way or this way, it not affect equilibrium point. So either sides can be equilibrium can achieved. Third, we can say initial concentrations. Initial concentration of reactants do not affect the relative equilibrium concentrations. And fourth, at equilibrium, pressure, color, concentrations, density, etc. will be constant. And if we want to achieve the equilibrium, then it has to be equilibrium can only be achieved in closed vessel. If it is open vessels, then what happens if the gases is present in the reactants, that will be evaporated, so you cannot achieve the equilibrium. So for achieving equilibrium, it has to be in a closed vessel. Next we derive the law of mass actions. Given by Goldberg and the two scientists. But they said that suppose reactions A gas and 2B gas. Is going to give 3C gas and 4D gas. What law of mass action says that, so here I am expressing this is known as active mass. This means active mass, or we can say this is concentration. So what he says that the rate of forward reactions which depend on the concentration of initial concentration, so rate of forward reaction. So we are going to this is the forward reactions. So this forward reaction depend upon this concentrations, so that is directly proportional to the concentration of A and concentration of B, and the stoichiometric coefficients will get power. And if I remove the proportionality constant, then I have to give some constant. Let's say this is forward reaction, so I will put Kf, that is equal to concentration of A, concentration of B square. Okay. Next, Similarly, for rate of backward reactions, it is directly proportional. So here backward reactions from here you are doing this here. So the backward reaction depend upon the concentration of C and concentration of D. Because backward reaction we are forming these two. So this means the reaction is happening. So the for backward reaction this is the reactant. So rate will depend the initial concentration. So for that these are the initial concentration. For the backward this is the product and this is the reactant. So rate of backward reaction. So rate of reaction depend upon on their initial concentration. So that will depend on concentration of C square. Sorry, concentration of. So this stoichiometry will get power and concentration of D to the power 4. So if I remove the proportional constant, we have to put one constant, that is Kb dq d4. So what at equilibrium, the rate of forward reaction equal to rate of backward reactions. At equilibrium, we know that rate of forward reaction equal to rate of backward reactions. So the rate of forward reaction is this, that is rate of forward reactions. Rate of forward reaction is this. So I can explain this Kf concentration of A B square. Rate of backward reaction this Kb concentration of Q d4. And if I say Kf by Kb, this is concentration of C Q, concentration of d4, concentration of A, concentration of B, and this rate constant is constant at a given temperature, and it will only change if you change the temperature. Otherwise, it do not depend on initial concentration. If you change the initial concentration, there will no effect on rate constant. It only change if you change the temperature. So this is rate constant, this is constant. So two constant, let us say another constant Ke. So Kf equal to Kb. So two rate constant if we divide, then we get another rate constant Ke. This is also depend only on temperature. So Ke is equal to concentration of Q, concentration of D4, concentration of A, and concentration of B square. So Ke equal to this. This is given by law of mass actions. And Ke we can express in two ways. One is Kc, another is Kp. And this is for liquids and gases. And this is for only gases we are using. So let's study the expression of Kc and Kp. So if the expression says like we have A gas plus B liquid give the C gas plus B of gas, then what will be the Kc? Kc will be the product concentrations divided by reactant concentrations, but not that concentrations of liquid is unit with gas molecules. Because the concentrations of liquids is huge in compared to concentrations of gases, because molecules of liquid molecules is high, very high compared to gas molecule. So we take as concentration of liquid with comparison to gas as unit. So this will taken as unit 1. So C is you can only write that concentration of C, concentration of B, and the concentration of A, because concentration of B is equal to 1. Another, here Kc equal to not 1. In this Kp will be, and Kp will be what? The Kp are expressed in the partial pressure of C, partial pressure of D, partial pressure of A. This is the Kp. Okay, and if examples, then here Kc equal to, this is taken as unit. So what? Concentration of solid is always taken as unit. So whenever concentration of solid is given, then we just take as unit 1, and that will not taken. So here Kp is not defined. Why? Because for Kp to define, at least one gas has to be present either in reactant side or in product side. So here gases is not present in both reactant and product side, so Kp is not defined. Another, suppose H2O. So here KCH so Kc will be concentration will be, so this is taken as unit. So if in aqueous medium concentration of water is taken as unit. Okay, so that's what it says. So Kc will become concentration of A, concentration of C, concentration of A, or we can, and Kp. So what will be the Kp? This is the Kc, and Kp is since no gas is present, so here not depend. Now next, the relationship between Kp and Kc. So let's take the example A gas plus B gas to give 2C gas plus 3D gas. So we know that Kc equal to concentration of product, that is the coefficient will be square, this, and we know that we want to derive the relationship, so let's use the ideal gas, that is Pv equal to nRT, then P equal to N by V RT. In a concentration, that is concentration is molarity, so molarity is moles per volume, moles per volume. So this N by C can explain as CRT. So I just want to know that this is the concentration, this what derive the concentration. So instead of this I will put like this, C square, C D square, C A square, C B square. Next what you know, Kp equal to, we express in the partial pressure. So this is the reactions A pretty gas. So Kp you are expressing the partial pressure. So partial pressure of C square, partial pressure of D Q, partial pressure of A, partial pressure of B, and we say that P equal to N by V RT. So P equal to CRT. So I just express that P term CRT. So I will write P as CRT. So C, that is C RT square, here C, that is D RT square, there is C A RT, C B RT. So now what he says, C square and CD, this is Q, CDQ, and this RT square and RTQ, I will take it out, and similarly CA and CD, then I will take out RT and RT. So observe the C square, CDQ and CCD, this is equal to Kc, this is Q. So this, so this is this, so this value and this value is same. So what I put, Kp equal to Kc, and it's RT square RTQ, RT and RT. So this RT square, this RT square and RTQ is coming from and this RT square and this Q, this is coming from product. So this is coming from product and this is coming from reactant. So what I said, RT, this is pipe, this is RT square, KC, RT. This is coming from product, this is coming from reactant. So I can write Ng, where Ng equal to, that is product, this is coming from product side, so product minus reactants. So Kp, you can say Kc equal to RT delta Ng. This is the derivation. So next class we will discuss some numerical problems. So today, after this, thank you.